All right, good morning, guys. I'm going to get started right away, and I'll take attendance at the end just because I feel like I'm going to need any minute I can get just to get everything in. The next section, I kind of already told you in section 1 that when you're proving those compositions, f of g of x, g of f of x equal x, when you're proving those equal compositions, you're basically proving that the two functions you composed are inverse functions. So, but we didn't call them inverse functions yet, right? So section 2 is all about inverse functions and one-to-one functions, all right? So since an inverse, by definition, is a function, I want you guys to remember what it means to be a function and all the different definitions that kind of brings up. So first of all, a function is a relation where each input has exactly one output, right? That's a relation where the x's do not repeat. That's usually how we would look at a relation. We would look to see if the x's didn't repeat, then we would know that that relation represents a function. All right, at the end of the day, a function, it's an input-output machine. You plug something in, the function does something to that number, and then it spits an output out. All right, excuse me. The way we work with a function generally is x is our input, x goes into the function, and then y, or now that we're in big bad fancy pre-calc, f of x comes out of that function, and you can start building that relation, building that set of ordered pairs, right? Okay, and then again, every time I think of a function, I can't not think of it this way. I go back to elementary school and I think of the machine, right? The function machine. You plug an x into the machine does something to that input, and then it spits the output, the y out. And you create all of those ordered pairs, all right? Okay, the graph of a function, because the x's don't repeat, the graph of a function will always pass the VLT, the vertical line test. If you can draw a vertical line anywhere over that graph and it only touches that graph one point at a time, that means it's a function. That test is proving that the x's didn't repeat. It's proving that each input only had one output. All right, and then a function, now that we're in pre-calc, a function is usually given to you as a written rule or an equation. F of x equals x squared minus 5, right? It's usually given to you as some type of written rule or equation. But remember, it can also be given to you as a graph, a list of ordered pairs, a table, a mapping diagram. These can all represent functions, all right? Okay, so that's what it means to be a function. So an inverse, by definition, is a function and has to behave like one. So all of these rules have to apply to the inverse, right? Okay, so let's go to what is an inverse? So let me give you the fancy schmancy definition first. Thanks, Michael. Hello. The fancy definition says, an inverse function says, suppose that f is a one-to-one function. We're going to go over what that is. If f is a one-to-one function, then corresponding to each x in the domain of f, there is exactly one y in the range because f is a function. Guys, that's how a function works. Each x goes to one y value. That's each input has one output. That's just what it means to be a function. And corresponding to each y in the range of f, there is exactly one x in the domain because f is one-to-one. So again, we kind of have to go over what it means to be one-to-one, but in a nutshell, what it's saying is that now each y only goes to one x. If you were to work that function backwards, each y value in the range only points to one x value in the domain. Because remember, to be a function, only the x's were not allowed to repeat. It didn't matter if the y's repeated. That was still a function. But an inverse is saying that it needs it to be a one-to-one function so that the y's aren't repeating either, is what that basically means. All right? The correspondence from the range of f back to the domain of f is called the inverse function. So basically, the inverse is going to take the original function and work it backwards. It's going to work from the original range back to the original domain. All right? F is then called the inverse function of f. The symbol, it looks like f to the negative 1 is used to denote the inverse of function f. But guys, we read that as f inverse of. F inverse of. Is that how we read that f to the negative 1? All right, so guys, let me give you a much easier definition as what it means to be an inverse. An inverse is a function that undoes another function. That's his job. The inverse is meant to undo whatever the original function is doing to something. So an inverse function undoes, very technical math word, undoes another function. That's what an inverse is. He is meant to undo all existing operations in the original function of f. And let me just put a little note. By definition, I keep saying that the inverse is a function. So therefore, it must follow function behavior. Specifically, a function says that when one number goes in, only one number could come out. That's a function. A function would never plug a number in and spit two different outputs out. That's so against what a function does. So your inverse has to behave that way. So guys, there are going to be limitations. There are going to be functions that do not have an inverse because they simply can't be reversed. So just know that only a certain kind of function actually ends up having an inverse. All right, so for example, let's look at what an inverse is going to look like. For example, let's say I plug 9 into a function and I get 14 out. That creates the ordered pair 9, 14. Well, the inverse's job is to undo everything that original function does. So if I take the output 14 and I plug it into the inverse, it should undo all of the operations that happened to 9 to get to that 14 and bring you right back to the 9. It should spit out the 9. It's going to undo everything the original function did and spit out that original x value. So now the point 14, 9 would be on the graph of the inverse. So basically, 9, 14 was how the original function worked. 14, 9 is how the inverse is going to work. It's going to work the original function backwards. So in a nutshell, the inverse will reverse the original ordered pairs. So guys, if it's going to reverse the original ordered pairs, that's a problem for some functions because some functions have y values that repeat. And if I reverse the ordered pairs, if those y values got repeated, that means those y values, when you go to spit them into the inverse, they're going to spit out multiple outputs, and that's not okay. So it's very restrictive as to what functions can actually have an inverse that exists, okay? So we have to kind of go over, well, what kind of functions can have an inverse then if they're going to reverse all those ordered pairs? All right, so just to kind of sum up how the original and the inverse are going to work. X goes into the original function and y comes out, right? Therefore, xy 9, 14 will always be a point that lives on the original function's graph. But then the inverse is going to undo that. So the inverse is going to take the original output as its input. It's going to plug in the original output. The y is going to go into the inverse function, and it's going to undo everything and spit out the original x value that we all started with. So now that means the point yx, the 14, 9, is on the inverse's function's graph. So therefore, the x and y, they trade roles. The original x's become the y's of the inverse. The original y's become the x's on the inverse. They literally trade roles. His inputs are this one output. This one's outputs are this one's input. They literally trade roles. So guys, just a little bit of a spoiler for the next day. Not only will x and y trade roles or trade spots in the ordered pairs, they're also going to trade roles in the equation too. All right, so the original function's y's or outputs become the inverse's x's or inputs. The original function's x's or inputs become the inverse function's y's or outputs. They literally switch. They literally switch everything. So guys, that means this one's domain is his range. This one's range is that one's domain. Even their domain and range switch. Which is kind of nice because if you know the domain of the original function, then you automatically know the range of the inverse because his domain is the inverse's range. All right, so since an inverse function will reverse the ordered pairs, only a one-to-one function can have an inverse. This is what I'm talking about. Because the inverse has to behave like a function, only a one-to-one function can have an inverse. If we go to switch the ordered pairs, you want to make sure that the y's didn't repeat either. Otherwise, if the y's repeat, the inverse won't act like a function. And I'll explain that in a minute. All right, so What is a one-to-one function? A one-to-one function is the only kind of function who can have an inverse that exists. A one-to-one function is a function where each element of the domain corresponds to exactly one element in the range. So basically this is saying 1x goes to 1y. The x's don't repeat. That's normal function behavior. And it's a function where each element in the range corresponds to exactly one element in the domain. So basically now it's saying if you were to look at the ordered pairs in reverse, each y value only points to one x value as well. So guys, basically in a nutshell, it's a function where the x and y's both don't repeat. If you are a one-to-one function, then your x's do not repeat and your y's do not repeat. This way, when you start reversing ordered pairs, everything is still acting like a function. And then the graph of a one-to-one function, yeah, it'll pass the vertical line test because it's a function. It's got to pass the vertical line test. The x's should not repeat. But guys, the graph of a one-to-one function will also pass the HLT, the horizontal line test, which means if I was to draw a horizontal line anywhere over the graph of that function, it would only hit the graph one dot at a time. The HLT is proving that the y values do not repeat. The VLT proves the x don't repeat. The HLT proves that the y's do not repeat. Because again, only a one-to-one function, a function where the x and y's both don't repeat, can have an inverse. This way, when I switch those x's and y's, nothing is not acting like a function. All right, let me move it up. Casey, okay? Am I moving? You all right? All right, so guys, what I did is I gave you 1, 2, 3, 4 functions, 2 mapping diagrams, a list of ordered pairs, and a mapping diagram again. All right, I want you guys to determine who's a one-to-one function and who's not a one-to-one function. Remember, if you are a one-to-one function, your x values don't repeat and your y's don't repeat. So look here. Here's a function, right? We have each x only being used one time. So if I was to ask the question, hey, when 8 goes in, who comes out? The only answer to that question is 11. If there was another arrow coming away from 8 pointing to the 4, that wouldn't even be a function. Because when I ask the question when 8 goes in, who comes out, there's 2 different answers to that. And that's not how a function behaves. So right now the x's don't repeat, that's a function. But inverse though, the inverse is gonna work this way. The inverse is gonna work backwards. It's gonna take this y value as its input. It's gonna plug a 4 in and it's gonna spit a 2 out. So you wanna make sure that these y values don't repeat because when you go to use them in reverse, if the y values repeat, that's not acting like a function. Let's say 2 numbers pointed to, I don't want to do that. Let's say this, let's just do that. If the y value was being used twice, right? Pretend 9 didn't point to 1. If 9 pointed to 11, if this y value was being used 2 times, then when you go to use the inverse in reverse, when I go to plug 11 into the inverse, then there's 2 numbers that inverse could spit out. When 11 goes into the inverse, he could spit out an 8 or he could spit out a 9. That's not a function. So you don't want the y's to repeat so that when you use these ordered pairs in reverse, they still act like a function. All right? So since each y is only used one time, that's a one-to-one function. This is a function where the x and the y's do not repeat. It's one-to-one. All right, look here. This is a function. Each x value is only used one time. If I asked a question when 9 goes in, who comes out, there's only one answer to that question. If I said when 8 goes in, who comes out, the only answer to that question is -1. All right, but do the y's not repeat? Is it one-to-one? Guys, this y value right here, he's used more than one time. So that means when you flip the ordered pairs and you use them in reverse, when -1 goes into the inverse, there's more than one answer to that question. When -1 goes into the inverse, he could spit out an 8 or he could spit out a 10. And that's not a function. So if the y's repeat, the inverse function is not going to act like a function. It's going to have more than one output for one input, and that's not okay. So this is not a one-to-one function, which means technically this function does not have an inverse that could exist because he doesn't act like a function when you reverse him. Does that make sense, Pace? Okay. All right, look here. Look at this function, right? This function says when -2 goes in, a 6 goes in, -1, comes out, a -1 goes in, a 3 comes out, a 0 goes in, a 2 comes out, a 1 goes in, a 5 comes out, a 2 goes in, an 8 comes out. Look at all your x's. Every single x is different. So that means each x is only used one time and it doesn't repeat. That's a function. So now look at the ordered pairs in reverse. Do the y's repeat? 8 goes into the inverse, a 2 comes out. 5 goes into the inverse, a 1 comes out. 2 goes into the inverse, a 0 comes out. 3 goes into the inverse, a -1 comes out. 6 goes into the inverse, a -2 comes out. Look at all these y values. They're all different. So the y values didn't repeat. So when I go to reverse it, it still acts like a function. That's one-to-one. The x's and the y's do not repeat. All right, look here. Here's a function. This is definitely a function. Each input only has one output. If I ask the question, hey, what's the cholesterol on a 46-year-old? There's only one answer to that question. Or what's the cholesterol for a 55-year-old? There's only one answer to that question. So it's a function, but is it one-to-one? The y's cannot repeat on a one-to-one function because when I use the function in reverse, if I said, hey, what's the age of a person with a 38 cholesterol? Well, the age of a person with a 38 cholesterol could spit out a 55 or a 61. That's not a function. If this input creates more than one output, it's not following function behavior. So since this y value gets repeated, it's not a one-to-one function. When I go to reverse these ordered pairs, the inverse will not act like a function. This input will create two different outputs. That's a no-go, not one-to-one. Okay? All right, so that's how you can tell if it's a one-to-one function when you're looking at the inputs versus the outputs, either in a list form or a mapping diagram or a table, whatever you want to do. What if you're looking at the graph? How do I know a one-to-one function when I'm looking at the graph? That's going to come down to your VLT and your HLT. Guys, thumbs up at home. Making any sense? Everybody okay? All right, here we go. So guys, if you were to look at the graph, I didn't put a graph on here because I figured we could graph them really quickly. This is the graph of the simplest version of a parabola, right? That has a x-intercept or a 0 at 0, and it's a bounce, right? It's a multiplicity of 2. So it looks like that, opening up. So guys, if you look at the graph of a parabola, we know it passes the vertical line test. So that says that each x only makes one y value come out. It says it's a function. But is it a one-to-one function? If it's a one-to-one function, not only will it pass the VLT, showing that the x's don't repeat, but it should pass the HLT. Can I draw a horizontal line anywhere over this graph and it only touches the graph one dot at a time? Well, no. The minute I draw a horizontal line, it touches here and here. That does not pass the HLT. That means the y values on this graph must repeat. But guys, we know they do. When 2 goes in, we know a 4 is going to come out, right? 2 squared, 4 comes out. When a -2 goes in, we know a 4 will come out. So we know the y's are repeating like crazy on the graph of a parabola. So now, it's still a function, but it's not one-to-one. If I was to reverse these ordered pairs, if I was to plug 4 into the inverse, it could spit out a 2 or a -2, and that's not a function. The inverse is not acting like a function, so it's not one-to-one. So technically, he does not have an inverse that exists. And you can sit here and say, well, wait a minute. If this function is squaring the input, I already know that a square has an inverse function. It's the square root. You're right. It does have an inverse function, but not over the life of this entire graph. You'd have to cut the domain to only part of that parabola to make the inverse exist. And that's what we did to make the square root function exist. We only put part of this domain into the inverse. And we'll get into that later. So we can force inverses to exist by restricting the original domain. But overall, over the life of this graph, he should not have an inverse that exists. So this is not one-to-one. All All right, what about the graph of x to the third, right? He has an x-intercept at 0 with a multiplicity of 3. A positive leading coefficient says he'd be up on the right and down on the left. And since he has a multiplicity of 3, it would kind of flatten out as it crosses over. Well, guys, is that a one-to-one function? Well, if I draw a vertical line, he passes it. I can draw a vertical line anywhere over this graph, and it only touches it one dot at a time. That's proving it's a function, right? The x's don't repeat. Does it pass the HLT? Because the HLT will prove that it's a one-to-one function. If I draw a horizontal line anywhere over this graph, it only touches it one dot at a time. So that's proving that the y values on this graph never repeat. So if I was to reverse these ordered pairs, since the y's don't repeat, they would only be able to spit out one x value in return. And that's a one-to-one function. His inverse is going to act like a function. All right, but there's a trick. This was not an increasing or decreasing function over the life of its entire graph. First, it's a decreasing function, then it turns and becomes increasing. But this is an increasing function the entire time. As x gets bigger, y got bigger the entire time. So guys, as long as you're increasing the entire time, y is always going to be changing, and y will never repeat. So there's a theorem that says a function that is increasing on an entire interval will always be one-to-one. A function that is decreasing. As x gets smaller, y will always be getting smaller, so y will always be changing and not repeating. A decreasing function on an interval will always be one-to-one. As long as it's constantly getting bigger or constantly getting smaller, you can say that that's a one-to-one function for sure. All right, perfect. Now let's put all this to good use. Okay, so I know that's a lot of fancy talk, but I'm telling you, working with inverses is really not that bad. It's just a bunch of switching. So look here. Find the inverse function of the following one-to-one function. So guys, they've given you a function as a set of ordered pairs, and they've already said to you it's one-to-one, so we don't have to worry about it. The minute you know it's one-to-one, you know the inverse can exist. So the inverse function would just be all of these ordered pairs, but reversed. We just flip them. So the inverse, let's say this is f. The inverse function then would be all these ordered pairs, but switched. If negative 3 went into the original and negative 27 came out, then negative 27 will go into the inverse and negative 3 will come out. So his ordered pair is negative 27, negative 3. All you do is flip them. So everybody do that. So that's the inverse function. All of the ordered pairs in reverse. So now they want you to find the domain and range of the function and its inverse. So let's do the domain of f. The original function, his domain are all of the x values. So all of the original x values, negative 3, negative 2, negative 1, 0, and so on. The range of the original function. The range of the original function are all of its y values. So negative 27, negative 8, negative 1, 0, and so on. Okay, now they want the domain of the inverse. Well, guys, the domain of the inverse, here's your inverse function. His domain, his x's are all of these numbers. Negative 27, negative 8, negative 1. So you can see the domain of the inverse is the range of the original function because his x's and y's literally traded roles. His range is his domain. His domain is the inverse's domain. I'm sorry, range. So now we're just going to list all of the x values of our inverse are here. Negative 27, negative 8, which again is this. Just take his range and make it the inverse's domain. And then the range of the inverse, well, here's our inverse function. The range are all of the y values, which are the same as the x values, the domain of the original. So again, if you already know what the original function looks like, if you already know the original function's domain or the original function's range, and you know it's a one-to-one function, then getting that inverse is extremely easy. You literally just switch the x's and y's. They trade roles. His inputs are this one's outputs. This one's outputs are this one's inputs. Okay. All right, well, guys, since inverse functions undo each other, we can say that whatever function f does, f inverse, the inverse of f will undo it and vice versa. Whatever the inverse does, the original will undo it. They undo each other. So therefore, we can say they're compositions. If I plug the original function into the inverse, all of those operations are going to cancel out and just leave you with x, as long as x is in the domain of f, because that's where you start. And same thing, if I plug the inverse into the original function, all of those operations are going to cancel each other out. They're inverses. They're undoing each other, and they're going to leave you with just x, your original input, as long as x is in the inverse's domain, because that's where he starts. So guys, when we were proving all of that f of g of x equals g of f of x equals x, what you were really doing with those two functions is proving that they're inverses. You were proving that they undo each other. All right, so this is how you are supposed to prove inverses. If you are given two functions, you can prove they are inverses by showing their compositions cancel each other out. Let me see if I can get through one example before the bell cuts me off. So look at this example. I know it's a little blurry. It's a picture from the book. I apologize. This is how we verify inverse functions. They want you to verify that the inverse of g of x, and they're telling you g of x is this function, x to the third plus 2. They want you to prove or verify that the inverse of this function is this function. They want you to verify that these two functions really are inverses and really will undo what each one is doing by showing that their compositions in any order both end up equaling x. So guys, we need to prove that when I plug the inverse into the original, everything cancels out and equals x. When I plug the original into the inverse, everything cancels out and equals x. And then we will be able to say that all operations are undoing each other. So let's verify this one first. Let's plug the inverse into the original function. So g of, who's the inverse? The third root of x minus 2. So we're going to plug the third root of x minus 2 into function g. So guys, go to function g, take x out, put the third root of x minus 2 in. And then it's got to be raised to the third power, and then we've got to add 2. What does the third power and the third root do to each other? Cancel. You're left with x minus 2 and then plus 2. What does minus 2 and plus 2 do to each other? Cancel. You're left with just x. When I plugged the inverse into the original function, all operations involved cancel each other out because they're inverses. They're inverse operations. They cancel each other. All right, but now let's prove that the other way works too. Now let's plug the original function, which is x to the third plus 2, into the inverse. So go to the inverse. It starts with the third root of, take x out, put x to the third plus 2 in. And then don't forget the minus 2 that's still under the radical. So guys, what happens to a plus 2 and a minus 2? They cancel. You're left with the third root of x to the third. What does the third root and the third power do to each other? Cancel. You're left with just x. So you have proven that these two functions in any order are canceling all of each other's operations out, and you have proven that they're inverses. So that's how you have to prove it. You can't prove it with numbers because you're just proving it for one case. You have to prove it with X so that you're saying it'll work for all X in the domains. All right, guys, I'm sorry that was a lot. I'm gonna do the last example and it'll be on the filled in part of your notes if you wanna look at that picture, okay? All right, let me double check the attendance, but you are good. Case, are you okay?